Welcome to EDU World Space.
So here again we have a uniform ladder that rests against the wall and it makes an angle theta. And we want to find the horizontal and vertical forces at the ground. Again, if a firefighter climbs on it. So this is basically the same problem as before, but we just don't have any. We're not given any quantities for our parameter values or our parameters, so we just have to do everything symbolically, which I would advocate doing to begin with anyway, and then plugging in parameters at the end, because then you can do some checks on your answers, and we'll do that in a minute here. So again, we know that the normal force here has to be the weight of the ladder and plus the weight of the firefighter. Okay, so that's just as we had before. In this case, I've used L, since they gave us L, the length of the ladder, instead of D1, which was half the length of the ladder. So we can take moments about this point again, so that, and again, this wall was frictionless, so this force is 0, and so this one will drop out. So, if we take moments about that point anyway. So we take moments, and we have the moment caused by the weight of the ladder, the moment caused by the weight of the firefighter. So this is the distance, and then the moment arm is, you need to multiply it by cosine of theta, and then the moment caused by the normal force and the moment caused by the friction force. So we have this. We can plug that into here and then solve for this, and what we get, if we divide through by g, is that F1 is minus L times M1 plus X times M2, all times cotangent of theta, all over 2L. So what can we say about this? Well, cotangent of 0 is infinity, so that is kind of a degenerate case here, and we would expect that some degeneracy, because of if this ladder were flat, then there's really nowhere where this friction force is acting. We can also see as the firefighter gets farther and farther up the ladder, the friction force grows in magnitude anyway. Likewise, as the masses of the firefighter and the ladder get greater, this grows in magnitude. So, and it's not clear as far as the length, because it's really the length over the x over L that is a parameter here. Here L's cancel out, so if we just increase the length, that would basically decrease the ratio of x over L, so it would make x effectively less. So this would actually be better to write this as m1 over 2 plus x over L, or x over 2L m2, and so we can see that x over L is actually the parameter that makes a difference here. And then we can also see if cotangent, if theta is 90 degrees, then this is 0, and we would expect that because then the ladder is vertical, and then there is no need for a horizontal force. And again, we can figure out what the friction coefficient is symbolically, and here we get that again it would, or what it would need to be anyway, and so we get that if the firefighter, if it were to slip when the firefighter was at a distance d up the ladder, we can see that it's 0 if theta is 90 degrees, again meaning that the firefighter could vertically go up the ladder as far as they wanted. And again, we can see that the critical thing here is d over L. I say so the distance, the percentage of the distance up the ladder the firefighter has gone. The masses kind of cancel out, not exactly, but you can see that as the masses go up, it's not clear about what how this friction coefficient would need to go up, because obviously the normal force then increases, so that even with the constant coefficient of friction, this force could increase to a larger value before slipping. Anyway, that's these are the answers symbolically.